Hey there, science fans! Today we're diving into the fascinating world of chemical equilibrium. Don't let the big words scare you. It's a pretty simple concept once you break it down. Imagine a group of kids playing tag. Some kids are running, some are hiding, and some are changing from runners to hiders and back again. Chemical equilibrium is kind of like that. It's like a constant game of tag between reactants, the things that go into a chemical reaction, and products, the things that come out. In a chemical reaction, reactants turn into products, but sometimes the products can also turn back into reactants. When the rate of the forward reaction, reactants to products, is the same as the rate of the reverse reaction, products to reactants, we've reached a state of chemical equilibrium. This balance point is super important in chemistry because it tells us a lot about how reactions work and what to expect from them. Now let's explore some real-life examples to make this even clearer. You might be surprised to learn that chemical equilibrium is happening all around us, even in our own homes. Let's take a look at a few everyday examples. Think about a bottle of fizzy drink. When it's sealed, the carbon dioxide gas, CO2, is dissolved in the liquid, but it's also constantly escaping into the space above the liquid. This is a state of equilibrium. The CO2 is going into the air and coming back into the liquid at the same rate. Another example is the evaporation of water. If you leave a glass of water out on the counter, some of it will evaporate and become water vapor in the air. But if you leave the glass out long enough, you'll notice that the water level doesn't just keep going down until it's empty. That's because the water vapor in the air can also condense back into liquid water in the glass. Eventually, the rate of evaporation and condensation will reach equilibrium, and the water level will stay relatively constant. These examples show us that equilibrium isn't about things being static or unchanging. It's about a dynamic balance between opposing forces. Let's delve deeper into this idea of dynamic equilibrium. Here's the thing about chemical equilibrium. It's not a boring, static state. It's a dynamic process where things are constantly changing, even though it looks like nothing is happening on a larger scale. Imagine a busy city street. Cars are constantly moving in both directions, but the overall traffic flow remains relatively stable. That's kind of like dynamic equilibrium. In a chemical reaction at equilibrium, the reactants are constantly turning into products, and the products are constantly turning back into reactants. It's like a two-way street where traffic is flowing smoothly in both directions. The rate of the forward reaction and the reverse reaction are equal, so the concentrations of reactants and products remain constant over time. This dynamic balance is what makes equilibrium so fascinating and important. It's a reminder that even seemingly stable systems are constantly in motion at a molecular level. Now, what happens when we mess with a system at equilibrium? Can we make it favor one side over the other? The answer is yes. That's where Le Chatelier's principle comes in. This principle, named after the brilliant French chemist Henri-Louis Le Chatelier, states that if a change of condition is applied to a system in equilibrium, the system will shift in a direction that relieves the stress. In simpler terms, if we poke a system at equilibrium, it will try to undo what we did and re-establish a state of balance. Think of it like a seesaw. If you add weight to one side, the seesaw will tip. But if you add the same amount of weight to the other side, it will balance out again. Le Chatelier's principle tells us that we can shift the equilibrium of a reaction by changing certain factors, such as concentration, adding or removing reactants or products, temperature, increasing or decreasing the temperature, pressure, increasing or decreasing the pressure, for reactions involving gases. Let's see how this principle works in action with a classic example. Did you know that diamonds are formed under intense pressure deep within the Earth? That's a dramatic example of Le Chatelier's principle in action. The formation of a diamond from graphite, which is the stuff pencil lead is made of, is a reaction that is favored by high pressure. When we apply a lot of pressure to graphite, the system wants to relieve that stress. It finds that it can do so by shifting the equilibrium towards the formation of diamond, which is denser and more compact than graphite. This is how those beautiful, sparkling gemstones are born. This example shows us how we can manipulate conditions to favor the formation of desired products in a chemical reaction. Pretty neat, right? Le Chatelier's principle isn't just for diamonds and fizzy drinks. It also plays a crucial role in understanding acids and bases. which are fundamental concepts in chemistry. You see, acids and bases exist in equilibrium with their conjugate pairs. A conjugate acid is what's left after a base has accepted a proton, and a conjugate base is what's left after an acid has donated a proton. Take water, for example. It can act as both an acid and a base. When it acts as an acid, it donates a proton and forms the hydroxide ion, its conjugate base. When it acts as a base, it accepts a proton and forms the hydronium ion, its conjugate acid. This delicate balance between acids, bases, and their conjugate pairs is essential for countless chemical processes, from the pH of our blood to the way our bodies digest food. We've already seen a few examples of reactions that reach equilibrium, but let's look at some more common ones. The Haber-Bosch process. This important industrial process produces ammonia, a key ingredient in fertilizers, by reacting nitrogen and hydrogen gases at high pressure and temperature. The reaction is reversible, meaning it can go in both directions, and reaches a state of equilibrium where ammonia is constantly being formed and decomposed. The dissolution of salts. When a salt, like table salt, dissolves in water, it dissociates into its constituent ions, which are in equilibrium with the undissolved salt. This equilibrium is why we can make saturated solutions, where no more salt can dissolve. The formation of rust. Rust forms when iron reacts with oxygen in the presence of water. This reaction is also reversible and reaches equilibrium. Understanding this equilibrium can help us prevent and control rust formation. These are just a few examples of the many reactions that exhibit equilibrium. As you delve deeper into chemistry, you'll encounter countless others. So why should we care about chemical equilibrium? Well, it turns out that this concept is incredibly important in various fields, including industrial chemistry. Understanding equilibrium is crucial for optimizing industrial processes, such as the production of ammonia, sulfuric acid, and many other essential chemicals. By manipulating conditions, we can shift the equilibrium to favor the formation of desired products. Environmental science equilibrium plays a vital role in understanding and addressing environmental issues, such as acid rain, ocean acidification, and the greenhouse effect. Medicine and biology. Our bodies are complex systems that rely on countless chemical reactions, many of which are at equilibrium. Understanding equilibrium helps us comprehend how our bodies function and develop new drugs and treatments. As you can see, chemical equilibrium is far from being a purely theoretical concept. It has real-world applications that impact our lives in profound ways. In conclusion, chemical equilibrium is like a delicate dance between reactants and products. It's a dynamic state where the forward and reverse reactions occur at the same rate, resulting in constant change at the molecular level while maintaining a stable balance overall. Le Chatelier's principle helps us understand how to shift this balance by changing factors like concentration, temperature, and pressure. This principle is a powerful tool for controlling chemical reactions and optimizing them for various applications. From the formation of diamonds deep within the earth to the delicate balance of acids and bases in our bodies, chemical equilibrium is a fundamental concept that governs countless processes in our world. So, keep exploring, keep questioning, and keep marveling at the wonders of chemistry.